where we're going to talk about the fundamentals of microservices. So thank you for joining NGINX's Microservices March series of webinars on the topic of microservices. My name is Owen Garrett. I work in the NGINX product group within F5, and I take joint responsibility for some of our microservices initiatives, our ingress controller, our service mesh, and the other approaches and technologies that we develop to help our users and our community get to grips with deploying and operating microservices applications. Just as we start, to help warm up and to give us all a little bit of an understanding of who's on this webinar, I'd like to run this short poll. What is your organization's expertise with microservices? Is it something that's completely new to you? You're here to learn about it? Is it something that's on your radar? Are you taking some first steps to deploy? Maybe you're running microservice and traditional apps in production, or entirely a microservices organization. While you complete this poll, we have with me my colleague Jen Gile, who's manning the chat, and she's very happy to share some codes for the NGINX Swag Store for anyone who shares questions or adds comments. So please stick around for that as well. Let's close the poll and see what we find. So there are a number of us on this session are running both microservice and traditional architectures in production. But there's also a sizable minority for whom microservices is something that's very new, either completely new or something which you're considering but are not operating yet, either in pre-production or production. So I hope this session is going to be useful to all of you as I go through a background of what microservices are and talk about some of the NGINX and F5 solutions that can help you build production-ready microservices. What is a microservice? Often it's very helpful to start with an analogy. And one of the analogies we could share is that building an application is a little bit like building a ship. In the 16th century in Europe, many countries in Europe were naval powers, and ships were built in place, large wooden constructions taking many months to build, with teams of craftsmen who specialized in particular aspects of the ship, laying down the hull, planking, caulking, decking, adding the rigging, and so on. It was a very, very skilled process, but it was slow and inefficient. At the time, Venice was one of the biggest naval powers in the Mediterranean, running over 3,000 ships, merchant and military ships across the Mediterranean. And they're widely credited as in being one of the first examples of an industrialized production line. This production line was known as the Venetian Arsenal. What you see is a present-day visualization of that arsenal, and it would build ships, producing a ship a day, the final outfitting taking just a matter of hours, and with over 100 ships and galleys in their backlog. If we look at an old illustration of the arsenal, it shows a little bit of how the process worked, with multiple different areas laid out for different purposes. Hulls would be built and stored, they'd go through a production process. The innovation that the Venetians are often credited to is the idea of a production line, where the object being manufactured is brought to the team, rather than the team gathering around the object, as other countries practiced when they built ships. But that's perhaps not the key innovation. If you zoom in and look in detail at this picture, you'll see that not only was there a production line for building ships, but individual components for the ships were built separately, independently, and then fitted to the ship or the galley as it flowed through this production line. The Venetians were not just the first industrialized production line, they were also the first to come up with the concept of interchangeable parts. And it was this concept of interchangeable, replaceable parts when they built ships that gave them huge benefits and advantages as they brought those ships to the sea, as they brought them to war, and as they maintained and upgraded those ships throughout their lifetime. A ship, like an application, is an expensive and valuable artifact. It's not something that you would throw away when it needs repair and rebuild. Just like your application, a working ship goes through a cycle of development, building, sea trials, deployment, and release, using it in practice. And that ship would regularly require upgrades or repairs or maintenance as new techniques came on board or as damage needed to be repaired. And by using replaceable, interchangeable parts, the operation of maintaining and upgrading that ship became much easier and much quicker. Within a day, a damaged Venetian galley can be brought into the arsenal, the rigging can be stripped off, the damaged masts and yards can be replaced, the rudder could be upgraded, all because the parts were designed to be interchangeable rather than being custom built for each individual vessel. And that is very analogous to how we build and manage applications. If you think of a monolithic application, which is built as a single unit, libraries and glue code is developed for that application and then links together and the application is deployed, then the task of developing, building, testing, deploying, and releasing this application and then iterating through changes becomes very, very laborious. Releases from start to finish can take months. Major development can take months as well. It's very difficult to fast track a new feature or a bug fix for this application and push it out into production because it's such a large, complex, heavyweight object, if you like an English or a French vessel of old. The goal of microservices is, just as the Venetians separated their vessels into small, interchangeable parts, the goal of microservices is to separate an application into small, interchangeable, replaceable parts. These parts can be developed, built, tested, deployed, and released independently of each other, in parallel. And the smaller and simpler a part is, the faster you can iterate around this cycle of developing through to releasing an application component. This is the thinking behind microservices. Businesses face the challenge of releasing applications quickly and iterating, bringing new features to market very, very fast. And the microservices architecture is an approach that tries to accelerate that process by decomposing an application into loosely coupled, independently deployable smaller services, like the independent components and capabilities on our Venetian galley. Each component is highly maintainable and testable. It's small, it's well-defined, it's self-contained. Components are loosely coupled. They use a straightforward API, a REST or a messaging API, to communicate with each other, meaning that the implementation of the component is hidden from the consumer. That makes it possible for the developer to change the implementation and replace the component without the application, the services that depend on that component having to synchronize. They're independently deployable. Standalone, they have their own dedicated technology stack. They can be deployed, upgraded, and scaled independently. Good practice is that these components are not simply pieces of technical functionality, but they're organized around business capabilities, user management or inventory management or image rendering. That good practice means that these components can naturally be reused in other applications, just as in our case of the Venetian galleys, anchors that are built for a war galley of a particular size can also be reused on a merchant ship of a similar size. And finally, in a microservices architecture, the components tend to be owned by a small team. This is a goal in the architecture. It's often described as the two-pizza team goal. It's well understood that teams of less than 10 engineers can operate very, very efficiently. without the overhead of communication that you find in larger teams. But building and deploying an application using a microservices pattern can be a lot more difficult than the processes that we're used to and accustomed to. Let's take another poll. I'm curious to know from our audience today, for those of you who said that you are deploying and operating microservices in production, what do you find are the biggest concerns that you have? Is it around training and knowledge? It's a new approach. It's very, very difficult to learn the skills. Are the challenges you find in production around visibility? Maybe around security? Or maybe in production, the challenges of running with large applications in multiple teams? Or are you one of the few unicorns who are very, very confident with what you're doing? You feel that you know what you're doing, everything's working, and you're satisfied with the processes that you have for operating microservice applications. Let's see what the result is. Let's give it a second. And we'll see how people have voted. So yeah, we're finding, as we find with many other audiences that we speak to, that although the promise of microservices is real and people capture what that promise is, the reality of getting there is difficult. And the challenge of getting there being difficult is because there are a lot of new technologies, a lot of new processes, and a lot of new ways of working that you need to get on top of. You're changing the architecture from a classic, well-understood monolithic architecture to a distributed microservices architecture. You're using different protocols. They're simpler, they're more lightweight, but there's a learning curve. The way that you look at the applications are different, the way that you automate, and the way that the culture that you need to support those applications is different. There are some pieces of technology that have emerged as being key to almost every microservice deployment. And as we're talking through the fundamentals, let's just stop and reflect briefly on these two pieces of technology. The first piece of technology that we see in just about every microservices initiative is the concept of a container. As we think about microservices and we think about interchangeable, replaceable parts, the way that those parts are packaged is really important. If we have the right format for packaging those parts, then it's easy to replace one part with another. And the format that's emerged is that of a container. You can think of a container as being a very, very lightweight virtual machine, but so much more lightweight that it allows new ways of working. A container takes the bare minimum that you need for an application, and it packages it up as a single artifact with the application code and runtime, any unique libraries that particular service requires, and a specification of the dependencies, the networking, the storage, the memory, the CPU that this container needs. And the great thing about a container is that it's very, very quick to build, and it is typically very, very small in terms of size. It's not like a virtual machine. A container is small enough that you can store it inside some sort of repository. You can copy it across the network. You can deploy it to the cloud without the overhead of having to move multiple gigabytes of data. And for that reason, people have developed pipelines where the code, when it's built, is packaged as a container. And that container then flows through the rest of the CI/CD pipeline, where it's tested, it's deployed, and it's operated. So that becomes your deployable component, your replaceable part. And a container needs to run on some sort of runtime platform. The runtime platform that's emerged is, of course, Kubernetes. Kubernetes is not the platform in its own right. Kubernetes is an orchestrator that brings together lots of different technologies. With Kubernetes, you have a master, which provides the APIs and schedulers and the various operations to run the Kubernetes environment. And you have a series of nodes. These nodes are where the containers run. Kubelet is a service that's used to push things to control nodes. And kubeproxy is another service that sets up a flat network across these nodes onto which the containers are deployed. They communicate over that internal flat network. For external access, for a user to access the service from outside, then there's typically an ingress controller, which provides a bridge between the internal network and the outside world. And there may be multiple tiers of infrastructure data plane, load balancers, web application firewalls, DNS systems that control how traffic is routed to the ingress controller. If you were to think of a production-grade Kubernetes environment, then there are three aspects that you'll want to consider. First of all, we can look at the developer's workflow from code to platform. And there is a large, almost confusing selection of technologies that you can pick from in order to build the pipeline that takes your application, packages it up as a container, puts it in some sort of artifact repository, implements a pipeline with testing and automation to push that container, or in Kubernetes speak, the pod, onto the runtime, and at the same time, automatically configure the data plane in front to route traffic to the application. And in parallel, you'll think about the operations challenges. Once the application is on that environment, what needs to be done in order to effectively operate it? How is security automated? How is authentication automated? How do you monitor and instrument the application? And how do you handle the logs from the application components? The users, so this is the third part of our story, the users access the application through a series of data plane components. There may, as I mentioned, be infrastructure-centric data plane components, edge firewalls, edge load balancers, DNS, and global traffic management solutions. And then there will be application data plane components. These components are tightly integrated with the application itself. So as applications are pushed to Kubernetes, the application data plane is modified and managed as part of that process. Operating an application in an environment like Kubernetes is hard. Again, you're going from a stable, predictable, well understood environment, a monolithic environment, through to an environment that is dynamic and distributed with many more moving parts, much more automation, and perhaps most scary of all, the temptation to run everything in production on the production platform, to push and upgrade services live in production. So when things do go wrong, they go wrong with live traffic on a live platform, and finding and debugging and resolving the faults becomes really, really critical. In order to do this, in order to achieve stability and predictability and a true production-grade environment, the key thing that you need to be able to understand how to automate and control is the data plane. This is the thing that connects end users to the individual services of your microservice application and also connects those individual services to each other. And so, for the rest of this webinar, we're going to talk through a couple of the technologies and the practices that you would use in order to automate and scale and control the data plane to give you predictability and performance for your distributed microservice application. Let's begin with the first part, which is colloquially or often described as the ingress controller. An ingress controller is a discrete piece of software. There are a number of options, and we'll take a little pause here for another poll. And I'm curious to know, for those of you who are running applications in Kubernetes, what ingress controller do you use? Do you use the standard ones that come with the Kubernetes environment? Maybe, as some of our users do, you're running OpenShift and you use the OpenShift router for that environment. Nginx, we have our own ingress controller based on Nginx open source and Nginx Plus, which I'll talk about shortly. If you're running an F5 Big IP device, you can use Container Ingress Services, CIS, to use the Big IP as the front end. Or maybe you're using something else. Or if you don't know, often that's below people's radar and they're not always aware of what's being used in production. Let's see what people say. So close the poll and let's get the results. And we find a lot of people don't know. The ingress controller is something which is not in your radar. It's not something you think perhaps is worthy of concern. But we do see that there's a lot of people using, for those who do know, it's well spread between either using the default ingress controller or router that came with the platform, or the one that Nginx provides. Why is an ingress controller important? Why should you know what you're using and care? Well, not all ingress controllers are alike. The ingress controller is a specialized load balancer that's designed specifically for Kubernetes environments. It's different to a regular load balancer because it's deployed in a different way. It bridges the external and internal networks in the Kubernetes platform. It's configured using the Kubernetes API, using objects called ingress resources. Doesn't have a GUI, you don't edit config files, you access and manage it through the Kubernetes API. And it integrates with the Kubernetes databases and processes, the service discovery layer. It learns where things are in Kubernetes, and it automatically updates its load balancing rules. If, for example, a service scales, so more replicas are added, or individual pods fail the health checks that Kubernetes runs against them. So an ingress controller is a really tightly integrated load balancing solution with Kubernetes. But we find that customers face several challenges when they start to run at scale. Kubernetes is a complicated environment, and even more so, people try and do complicated things on Kubernetes. So the needs of complex applications and workflows can put a strain on the capabilities of the ingress controller. And additionally, Kubernetes is often used in a shared fashion, multi-tenancy, many teams collaborating and cooperating on a single Kubernetes platform. And those teams need to be able to cooperate and share the environment, including the ingress controller, safely and securely. We've put a lot of engineering into the Nginx ingress controller with the goal of making it easier to meet those two challenges. We have a rich but straightforward and natural way of configuring the Nginx ingress controller with the concepts of virtual servers. These are objects you publish to Kubernetes that represent your application and the rules that should be used in order to route traffic to that application, including rules that can do things like respond directly if a user enters the wrong URL, redirect to a different service, proxy across multiple different services, and we allow you to take that configuration and split it up and delegate it for reasons that will become clear in a moment. Because the ingress controller is built on Nginx, it also has the capability of using many of the advanced features within Nginx, things like access control or the web application firewall. And these are configured through separate standalone policies that can be referenced from the Nginx ingress resource. There are always edge cases, special cases, unusual use cases where people need to do something which goes beyond the schema that we've designed with virtual servers and policies. And in that case, we make it easy for people to directly edit the Nginx configuration by adding snippets in various places. This rich way of configuring the ingress controller means that we can meet many of the complicated use cases that are referred to. Conditional routing means that you can run dev and production workloads in production and switch traffic based on, for example, where a user is coming from or the cookies that they have. Rate limiting allows you to protect applications that might be vulnerable to spikes of traffic, or to limit greedy clients that might be trying to, for example, crawl an API and send large numbers of requests. The integrated web application firewall lets you protect from a range of attacks against known and unknown vulnerabilities, and to do that on the ingress controller. So with the Nginx solution, you get a much richer set of functionality than you would with competing solutions. And this allows you to better use Kubernetes and operate your microservices applications. But we did point out that Kubernetes is often used in a shared fashion. Multiple users have to cooperate and collaborate in order to build a configuration. And our ingress resources are designed to support those use cases. So for example, an identity team in one namespace can define the WAF policies or the access control policies. Individual application teams have access to their specific configuration, but they don't have access to the NetOps-centric configuration that might represent the SSL termination and the endpoints, the entry points for applications. By being aware of namespaces and assembling the configuration flexibly across multiple namespaces, the Nginx Ingress Controller allows you to meet some very, very complex and sophisticated use cases in a secure, scalable, and manageable fashion. The Ingress Controller gives you great control over traffic coming into the application, but as you operate a microservices application on a Kubernetes platform, you'll find that many of the operational challenges that you face happen from within the application, not from the north-south traffic coming into it. And for this, the standard response that the Kubernetes community will give as to how do you address these complex use cases is to use a service mesh. Let's take another poll. A service mesh is an emerging and complex piece of technology. And I'm curious to know, of those in the audience who are running in Kubernetes, are you using a service mesh in production now? Is it something you're evaluating? Or are there other ones? Send things in the chat and let us know. Or if you don't know, that's a great answer too. So let's close this poll and see what's our audience's awareness and usage of a service mesh now. So a lot of people are not aware as to whether or not they're using a service mesh. There are, 20% of people are actively evaluating. A few people aren't and don't have any plans. Of the ones in production, then Istio is the most common one in production, and that resonates and chimes exactly with what we see when we talk to users in the field. A service mesh is a new piece of technology. Istio was one, not the first, but one of the early movers in service mesh technology, and their open source solution is currently one of the most widely deployed. When you talk about traffic and controlling the data plane in a Kubernetes or microservice environment, often you'll hear the terms north-south and east-west. North-south refers to the ingress and egress traffic coming into the application from outside. And that traffic, as we've seen, is well handled by the Ingress Controller. It provides a secure and reliable and persistent front end that users talk to in order to access the application. But the Ingress Controller rarely has a role to play for the east-west or internal traffic within the application. In our distributed microservice application, the Ingress Controller might forward a request to a front-end web UI, for example, but that web UI will need to talk to multiple other services using internal east-west requests. And the service mesh aims to improve the observability of those internal transactions, providing ways to control those transactions, to observe and monitor what's happening, and to layer security onto the transactions. Service meshes are new bits of technology. The processes and architectures are still emerging, and solutions like Istio tend to be very heavyweight and complex. The experience that we've heard from the field is that large organizations find there's a steep learning curve and needs to build a lot of internal expertise to operate something as complex as Istio. The mesh works by intercepting and controlling all the transactions between individual pods in the Kubernetes environment. And the mesh may perform a number of different functions. It may secure those transactions by automatically encrypting them using mutual TLS or access control lists, so that it's not possible to snoop or impersonate transactions, and the mesh applies a strong security allow list and deny list approach to permit and deny traffic. The mesh will provide orchestration. It should integrate with the Kubernetes API, not be a standalone independent tool with its own APIs and its own management tools. By controlling traffic, the mesh can then manage all of the different use cases. So load balancing, circuit breaking, rate limiting, blue-green deployments, and with observability, a mesh should be able to measure the traffic, generate traces, provide real-time monitoring. A typical mesh is architected using a sidecar proxy approach. And here we're showing the architecture of the Nginx service mesh. Our service mesh is in public beta at the moment, with a GA release planned for the next, for the near future. And it is architected in a similar way to other contemporary service meshes. It works by auto-injecting a proxy into each individual pod or container on the Kubernetes environment. This is the sidecar proxy. We automatically inject Nginx Plus, and that proxy captures and manages all traffic coming into the pod and all traffic going out. We configure the proxies using a mutual TLS provider. We use Spire to manage the SSL certificates, to securely distribute the certificates and then encrypt the traffic between individual servers. We integrate with the standard Kubernetes ecosystem tools, Prometheus Grafana for metrics, open tracing for trace information, and with an API that's integrated into the Kubernetes API, you can then configure the capabilities that you want the mesh to apply. The allow lists, the deny lists, the advanced load balancing, the blue-green, the rate limits. Our mesh integrates cleanly through a common API with the Nginx ingress controller to perform ingress and egress functions for your environment. And this is very typical of other service meshes of this type. Just as the ingress controller allows you to implement certain use cases, a service mesh lets you implement use cases within the application. Mutual TLS lets you implement secure traffic. Tracing lets you easily debug transactions, understand the fan-out and cascade that an incoming transaction causes within the application, and pin down on faults, either services that have failed or services with a high latency, where that latency then ripples through to create an overall latency burden. Or egress control. Use the service mesh to broker the traffic to external services to limit which services an application can talk to and the kinds of requests and transactions that they might send. As I mentioned, service meshes are a very new technology, and I would not recommend them for everybody at this stage. If you have a mature, fully automated CI/CD pipeline, so often described as GitOps, that I would say is a prerequisite for thinking about a service mesh. It's not a technical prerequisite, but it's a practical prerequisite. Service meshes are designed to solve problems, but if you haven't automated your CI/CD pipeline, you've got bigger problems already that a mesh can solve. So fix that first. Current service meshes are tightly focused on Kubernetes, so you need to be fully invested in microservices and Kubernetes to get full advantage from the service mesh. Meshes are designed to solve problems, or at least identify problems that come from fast-changing, fluid environments. If your applications are stable and well understood and you're not deploying frequently to production, you probably don't need a mesh. You probably understand the application well enough that the complexity of a mesh is not going to bring any additional benefits. If you don't need mutual TLS, then you may be able to get away without using a service mesh, because there are other ways that you can layer some of this functionality on top. And if a mesh is appropriate if you do need additional visibility of traffic interaction, and it's too burdensome to build that into each individual service or pod using standardized interfaces like Prometheus or the open tracing libraries. Service Mesh promises to add those in a more industrialized fashion. Organizations often talk about the complexity of an application. My rule of thumb is that if the application is small enough that your developers and architects can mentally model that application and understand how it works in their heads from end to end, then they're probably better equipped for investigating and debugging and diagnosing problems with the application than a mesh would be, because they intuitively understand how the application is architected. But once you get to the point where maybe you have more than 20 services, the service depth is more than three services deep, at that point it becomes too difficult to fully model and understand the application. And that is the state at which you may consider a service mesh to help support your Kubernetes deployments. So as we wrap our fundamentals of microservices session today, what have we learned? Well, I would venture that we've learned that microservices is a journey. It's not a destination. You can't check the box to say you have arrived with microservices. There are always things to learn, there are always things to improve, and the underlying technology is changing very, very quickly. Begin with microservices when you're at the point that you need to iterate and improve your application quickly. If you are operating in an environment or a business where you're comfortable doing waterfall or fairly steady agile fortnightly or monthly releases, you probably don't need microservices. If you're operating that process well and it works well for you, then stick with the simpler, better understood monolithic approach. But if you're operating in an environment where you have complex applications and you need to iterate and improve parts of those quickly, you're running a Venetian fleet of galleys that need constant maintenance, then a microservices approach will help you scale. It's almost certain, as you look at this, the technology choice that you make will point you in the direction of containers and of Kubernetes as the core foundational technologies for a microservices initiative. Although it's very likely you will end up having a hybrid environment where some microservices are running on Kubernetes, but your application also depends on traditional monolithic workloads, such as a database or an inventory system, perhaps that you wrap with a simple API strangler pattern. The microservices journey is a long journey. Development and operations take parallel but separate paths as they consider the implications of adopting microservices for their respective roles. The key to making it work in production is to control the production platform using the application data plane. So technologies such as the ingress controller and perhaps the service mesh are critical to operating the application reliably, securely, predictably, and in a scalable fashion in production. To find out more, join us on our Microservices March journey. There's a great series of sessions from our users, from our community, from NGINX experts diving into different aspects of microservices. Today was our microservices fundamentals, or a little the basics, but you get expert advice on scaling and security on the other sessions on NGINX's Microservices March. So folks, thank you very much for your time today. I hope this has been useful and instructive. I've enjoyed seeing the responses to the polls, and I'm going to take a little pause and delve in and look at what's happened in the Q&A. And if there's anything in there, and please, if you have questions that this session has provoked, drop them into the Q&A and let us know, and I'll do my best to deal with them.
Hey, Owen, we've had a lot of activity in the Q&A. I'm going to go ahead and mark one of these for you to answer live from Ted. It says we have teams which follow Scrum and others which are traditional or waterfall. How important is following an agile methodology to success with microservices and Kubernetes?
Great question. So Ted, I think agile goes hand in hand with microservices. You could of course use a traditional waterfall model. Individual teams build their services in a waterfall fashion and push them out to production, but that's not getting the real point or benefit behind microservices. The reason people do microservices is because they want to be able to develop quickly and in parallel. They want to be able to build and develop. If we think of a Venetian galley, they want to develop the cannons independently of developing the rigging and the masts and the sails and the other components of the boat. And microservices allows you to break that application up into individually developable components and to use a fast process such as Agile to iterate fast. I've worked with waterfall processes in the past. There's always been a period that we call integration hell at the end of each waterfall cycle that can take months to bring all the different projects together. By putting a strong contract around how services are architected and the APIs that they use, the goal with microservices is to avoid that integration hell and smooth out that period.
Okay, we have another good one. I'll go ahead and Mark answer live here. What are the best options for using microservices other than Kubernetes?
That is a good one. And a couple of years ago, there was a plethora of options. There were cloud-based solutions such as Azure Service Fabric. There are various different application platforms that provided their own networking. But Kubernetes has very clearly emerged as being one of the dominant solutions. Sometimes people think Kubernetes is all I need for a microservices application. That's not the case. As I looked at the development and operations and data plane tracks of a slide a few minutes ago, there are a lot of attendant solutions that you need. But you tend to find Kubernetes at the center. Kubernetes' job is to orchestrate the environment where containers run, and there's a large number of ecosystem tools around that you need to learn. So it is complex. There are vendors, and Google are trying to build simpler Kubernetes environments. Other cloud providers are trying to automate and bring the Kubernetes environment into their walled garden. So there are options. Red Hat with OpenShift is trying to do something similar. But my advice is right now, there really is no other credible game in town unless you have some very specific use cases or requirements.
All right, we have quite a few other questions in here. I'll start with one from Paul. It says, aren't service meshes required for microservices as they orchestrate how the microservices are used by an app?
That's a very telling question, Paul, and it's something that I hear quite a lot. We even get users getting in touch with us at Nginx saying, I'm going to use Kubernetes, where do I get a service mesh from? And the problem we've seen is that projects such as Istio have been very heavily marketed. Istio by Google, other projects by other vendors. And it's given people the impression that you have to have a service mesh in order to run a microservices application. You don't. You do not need a service mesh to run Kubernetes or to run a microservices application. You need a service mesh to address some very specific problems that you might find with Kubernetes. Those are problems that typically you'll only encounter when you're running at a high level of scale. So I would say, don't let uncertainty about service mesh hold you back from going microservices. Proceed, decompose your application, put things on Kubernetes, run it in production. You will get to a point where you hit the problems that a service mesh attempts to address, but there are other ways to solve those problems as well. Talk to us at Nginx, talk to the community, focus on the problems you're trying to solve, not the silver bullet promise that a service mesh is going to fix them all.
All right, we have a question in the chat. It says, are there serverless options for implementing a microservices architecture?
Yes, there are. We have a near serverless platform called Nginx Unit. There are community projects inside Kubernetes to run serverless options. Cloud providers have serverless options. The point of a serverless option is that you can think of it as running the container or the pod on demand. If you have a particular lightweight operation, then you don't need to run a pod persistently. So look at some of the projects from the Kubernetes Foundation, from CNCF, look at what your cloud provider are doing, and you can integrate serverless quite nicely with a microservices environment.
All right, we have a number of other open questions in the Q&A. Let's see here. We'll start with one from Naveed. It says, I'm sorry, I'm not sure that it's a question, but I'll read it. The key to microservice success is to build independent and replaceable components of the application with a very precise methodology. Outcome is to build standard components. What do you think about that, Owen?
100%. Just as the key to the Venetians in running a fleet of 3,000 galleys and merchant vessels was to build boats in a very standardized, understandable way with replaceable parts. Yep, same applies to microservices. If you have custom snowflakes, it gets difficult. So look to standardize not just the frameworks that you use, but also interfaces like authentication, how you do rate limiting, the components that you use, and that way you'll find success more quickly with microservices.
And then are there competing standards for building standardized components for microservices? I think I just heard something recently about the National Institutes of Standards in the United States actually looking at this.
So there almost certainly are. I'm not aware of what's happening with NIST, but I know that many vendors have tried to create standards that converge around their particular ecosystem. There was an interesting question just beneath from Scott about how do microservices communicate with each other. And I would say look for standards around communication. Pick a standardized API. It could be REST, it could be gRPC. Pick a standardized message bus. You can use different libraries and frameworks for individual microservices. So one of your teams, the web team, might like to use Rails because that's particularly good for creating web front ends. Your analytics team might use Python. So one of the beauties of microservices is that you can be free to have different standards for each of your different small teams. Where you need to have standards is around the APIs and interfaces so that everybody can talk to each other in a standardized contract-based way.
Okay, we've got some more detailed questions in here. One from Scott. It says, how do each of the microservices communicate with each other? If HTTP, how do we handle network reliability and latency while ensuring high availability and user responsiveness?
Good question, Scott. So yes, HTTP is one of the common ways that microservices will communicate with each other, either with REST over HTTP or gRPC over HTTP. This is a good example of a standard that makes things easier for you as an operator. How do you handle reliability and latency? That's why it's so important to have control of the data plane that the application is running on. So that with ingress controller and maybe a service mesh, you can monitor reliability, you can monitor latency, you can monitor security, and then you automate the tasks that you need to fix any problems using the Kubernetes API. A great example might be a canary release, where you have an application running in Kubernetes and you want to upgrade it, deploy a new version of that application, and do that in a way that ensures the availability and responsiveness. With a canary release, you deploy a canary, the new application, and you route a tiny proportion of traffic to it using the ingress controller or the service mesh, and you monitor it for latency, for responsiveness, for correct operation, and then you control the application data plane. So you reconfigure the ingress controller, or you reconfigure the service mesh by changing weights to slowly up the amount of traffic that goes to the canary, and eventually move traffic across from the old version to the new version. That process is called a blue-green deployment. So by automating the data plane and using standardized protocols such as HTTP, you can address challenges of reliability and high availability and user responsiveness. With a smart ingress controller such as the Nginx one, it also brings in the capabilities learnt from managing production applications in other environments. So it can handle things like retries. It has smart load balancing methods to bypass underperforming pods within a deployment. So plenty of capabilities based on the expertise that we've built at Nginx for the last 15 to 18 years.
Okay, we have a couple of questions in here about moving from monolithic to microservices, dealing with what that movement looks like. What kind of resources or suggestions do you have for splitting your app into microservices, demarcating the boundaries, refactoring, etc.?
So there's plenty of advice that tends to converge around the same two principles. The first principle is that when you decompose your monolith, decompose it based on business function, not on technology. By decomposing it based on business function, so a function to manage users, a function to handle logs, then you'll end up with reusable components that are better architected. So that's one thing to bear in mind. The other thing to bear in mind, the other pattern that you commonly hear about, is the strangler pattern. And this says when you start to use microservices, you don't have to rewrite your application from scratch. Instead, wrap your application with additional services as needed. So maybe you have a large monolithic application and you need to expose a REST API for that application. Put a microservice in front of that application that implements the REST API. Maybe that REST API manages the inventory database in the application. So you create a microservice that presents a REST API for that business use case, and it talks to the application using whatever method necessary, screen scraping, directly accessing the database, whatever. So you're wrapping your application with individual services. You're, in a way, strangling the application. You're concealing the application from the outside world, so users access it through those services, and then in time, you can re-implement the functionality that you need in those services and bypass the functionality in the application. Martin Fowler is a great thought leader for microservices, and he's written a lot about the strangler pattern. So that'd be a great place to begin.
All right, and there was a question here about REST API where there was kind of a follow-up that said, what about events or messaging with Kafka and other high-performance messaging architectures?
Yeah, so these are the two different types of transactions that you will commonly see in a microservices environment. And the events are typically a pub/sub kind of model. Those won't go through the ingress controller. Those are internal. There's a much more mature and microservices-friendly set of technology for handling message buses and events. They tend to drop directly into a microservices environment in a way that REST APIs don't. So it tends to be simpler. We find that people have to focus on the ingress use case and the API use case most of all.
Okay, we have another question about monolithic and microservices. This time it says, can we have an application running in a hybrid environment where some parts are in microservices and some parts are monolithic?
Yeah, so yes, you can. And this is the most common use case. Organizations will very rarely take an existing application and lift and shift it into a Kubernetes environment. So yeah, you have components, maybe your original J2EE application running as a monolith, APIs wrapped around that. The bits that you're changing fast are written as microservices and are deployed inside Kubernetes. So this hybrid approach is very common. I just want to give a little shout out to Naveed. I'm looking at the questions go by, and Naveed is pointing out that Eli Whitney also followed the Venetian model. So yep, in the 19th century, they constructed rifles, and they also took the interchangeable parts approach. They famously Eli Whitney took 10 of his rifles, put them in front of Congress, took them apart, modeled all the pieces together, and then built them back again from the standardized parts and showed the benefits of using interchangeable parts. So that's another great example, following the Venetian model. And in fact, the Venetian model is known as the American style of manufacturing for exactly what Eli Whitney did.
Fascinating. We are starting to bump up at the top of the hour, and so if we don't get a chance to answer the remaining questions here, we will follow up with you afterwards. If you didn't notice in the chat, we have a survey running. We'd love to get your feedback on the session, hear a bit more about what you're doing with microservices and Kubernetes, and of course, give you the opportunity to enter our swag raffle or connect with our product management team. We won't use any of your info for sales or marketing. I think this question from Pushkar, will you suggest beginners with certain courses for microservices is a great way to start to close out this session. What should people do next?
So there's plenty of things to look at. There are the domain-driven aspects, the architectural aspects of microservices. So search Decomposing the Monolith, look at work from Martin Fowler as a great starting point. Chris Richardson as well is a good thought leader on the architecture of microservices. For individual bits of technology, learn K8s, anything that will help you get up to speed with Docker, containers, and Kubernetes. There's a plethora of solutions out there, and get to grips with a Kubernetes environment. Look at the CNCF, look at their landscape, don't be overwhelmed by the number of options, and start from there. Come and talk to Nginx. We can help with the architecture. We can absolutely help with the data plane part of the solution, which centers around the production-ready aspect of microservices.
All right, and if you are ready to try out either the Nginx Ingress Controller or the Nginx Service Mesh, we do have a free trial for the Ingress Controller. It's a free 30-day trial. And the Service Mesh is just free, always free. And so you can check out the chat for links to the pages where you can find out some more details about that. I do see quite a few more questions in here. And as I said, we'll follow up with you offline. I don't know that we'll get to all of these. Let's see if we've got a good closeout. I've seen lots of people asking for publishing resources, too fast to collect. Lots of questions about will there be a recording? And so yes, everyone who registered will get an email after the session that will include the recording as well as the slides that you see here today. And maybe this is good fodder for a future blog for our website, Owen, of getting started with microservices, right?
It will be, and there's some. I was scanning through the questions. There were some that unfortunately we didn't have time to answer that maybe we could build together into a blog, Jen, and get out over the next few weeks.
Yeah, sounds great. So let's go ahead and wrap it up there. Owen, thank you so much for your time and expertise as always, and everyone who's engaged and attended, great questions.